In today's video, we're going to consider the applications of probability generating functions. First, I'll just introduce you broadly to some of their applications, and then in the next several videos, I'm going to focus on each of them individually, those applications, and go into more depth. So without further ado, let's have a look at their applications and uses. So PGFs are useful for several reasons. And here they are. Point number one, alternative specification. Specification of the distribution. Now, what do I mean? Alternative specification of the distribution as opposed to the probability mass function / the cumulative distribution function. In other words, if it exists, the PGF uniquely determines the distribution. We'll go into that. We'll give a more mathematical definition of that. But for now, let's move on to number two. So, quite simply, PGF, it's kind of in the name, probability generating. It can be used to compute the probabilities of a distribution. Number three, it can also be used to compute the moments of a distribution. And by moments, of course, I mean the expected value of x to the power of n, where n is a natural number. Now, there's an important point here. Computing the moments with a PGF is actually computationally smart. It effectively avoids the complexity of, and I'll write that down, while avoiding the computational complexity of summation. Right, because if you think about it, if we were to compute the expected value of x to the power of n, that involves putting x to the power of n in our x formula for expectation, involves quite a lot of summation, a lot of computation. It's quite useful. It turns out that's sort of a stark contrast to point number two, where we could theoretically compute the probabilities of the distribution using the PGF. Turns out that's not as practical, and it's much more practical just to simply compute it from the PMF itself. Nonetheless, 2 is technically a property and an application. And finally, the fourth and perhaps most powerful application of PGFs, they can be used to analyze sums of random variables, and it's particularly useful for independent random variables. Because for independent random variables, when we sum them up, PGFs actually allow us to determine the distribution of the sum without using our methods of convolution. And that's a very powerful property. I'll go into that one, of course, in a separate video, but for now, let's focus primarily on point 1, that it is an alternative specification of the distribution. Let me formalize that more mathematically, and I'll call it this: uniqueness of PGFs. And here is the formalization. Consider two random variables, we'll say x and y, such that the probability generating functions px of z and px or py of z are equal to one another for all, let's say it's defined for some z less than or equal to c, absolute value of z less than or equal to c. It follows that, important property here, the cumulative distribution function, right, fx of z, and the cumulative distribution function of y are equal to one another for all z an element of R. Don't confuse the two z's here. This is the probability generating function evaluated at z. This is the cumulative distribution function evaluated at z, and it's applicable to all values R in the real number line. It's just a dummy variable in this particular case. In this instance, we can rewrite this perhaps more linguistically. That is, if two random variables, two RVs, share an identical PGF, then they also share an identical distribution. Quite an interesting property. So to sort of formalize this, or to understand this perhaps a little bit better, it's best to work through some examples. And to do that, what I'm actually going to do is I'm going to construct a table of common probability generating functions for common discrete distribution functions. And then we're going to use that table through an example and see if we can identify the distribution. So let me draw that table for you. On the left-hand side of this table, we have our distributions, or our common discrete distributions, namely the Bernoulli, the binomial, the geometric, the negative binomial, the discrete uniform, and the Poisson. And on the right-hand side of this distribution here, we have their respective PGFs. Now, in separate videos, I go on and describe how these particular PGFs are derived, but for now, take these at face value. However, if you are curious about their derivation, I encourage you to look at those separate videos on the channel. One thing, or a few things to point out here, is that where we have a distribution with a particular parameter, say here, for example, the Bernoulli has parameter p, the respective probability generating function, which is a function of z, also contains that parameter somewhere within its function. Similar negative, the binomial, n and p are the parameters. You can see n and p are also part of the PGF. Another point to please keep in consideration here, if you're looking at this, is that I have specified that the distribution of the geometric random variable here is the number of failures before the first success. It is not the total number of trials before the first success, and that comes out with this particular probability generating function. It is a different probability generating function if we are dealing with the alternative definition. Similar to the negative binomial, I'm defining this as the number of failures before the rth success, not the total number of trials before the rth success. And of course, for these two in particular, just keep in mind that the definition here, or the PGFs, actually have a specified possible range of Z values for convergence to be true. Keeping that in mind, now let's just go through an example. Here we're told that x is a random variable with probability generating function given by 0.4 over 1 minus z plus 0.4z all to the power of 5. And we have to determine the distribution of z. Well, let's look at our lovely table above and see if maybe we can find the distribution and look at which function closely resembles the one below. And immediately the one that spots out to me is there are two things that I'm looking for here. I'm looking for a power on the outside, and I'm looking sort of for a fraction on the inside. And the one distribution that does specify those prerequisites is the following here, the negative binomial. We've got a power on the outside and a fraction on the inside of the generating function. It's probably going to be this one. So firstly, I'm going to say when x has a negative binomial distribution with parameters r and p, then the probability generating function px of z we said was given by p1 minus z plus pz, close that, all to the power of r, where absolute value of z is less than 1 on 1 minus p. Now, if I specify p is equal to 0.4 and r is equal to 5, in other words, I'm trying to make it look more like this function, then the probability generating function px of z is equal to 0.4 over 1 minus z plus 0.4z all to the power of 5 for absolute value of z less than or equal to 1 minus 0.4. Therefore, by the uniqueness of PGFs, you'll notice x is a negative binomial with parameters 5 and 0.4. Let's go through one more example to solidify this. We're told x is a random variable with the following probability generating function. Determine the distribution of x. Well, here we notice that we have an exponential function to the power of some function of z. And if I look very closely here, we notice that the one probability generating function with an exponential function within its definition is the Poisson distribution. So in a similar fashion to before, I'm going to note when x has a Poisson distribution with parameter lambda, then the probability generating function px of z is by definition e to the lambda z minus 1. And we note when lambda is equal to 3, let me fix that lambda, it was a very ugly looking lambda. Lambda is equal to 3, then this probability generating function z is equal to e to the 3z minus 1. Hey, what do you know? This looks exactly like the probability generating function we need to find. Therefore, by uniqueness of PGFs, x has a Poisson distribution with rate parameter 3. There concludes the video. I hope that in this video we've solidified what this definition of uniqueness of PGFs means and how it can be used to determine the distribution when given the PGF. In the next video, we will look at computing the probabilities using the PGF, and in subsequent videos, we'll look at properties 3 and 4, applications 3 and 4. Thank you for watching this video. I hope to see you in the next one.